Hello everyone, welcome to Paper Muni. I am Biplab Datta and I am teaching you quantum mechanics, and this is your 17th lecture.
Good afternoon, sir.
Good afternoon. How are you all?
Sir, good. It's
Great.
cold out there.
I feel a little bit more. All right. So that's why the cap. Okay. So what we did so far was sorry. What we did so far was we discussed the wave acceptable wave functions. We discussed 1D potential. We discussed 2D potentials. Okay, we discussed operators. All right. So what we'll do is today solve some problems related to this thing. Your this 1D and 2D and 3D potentials. All right. So or maybe some problems from operators also. All right. So we'll have this will be like uh, a revision session. Okay, so let me get the question first. All right, so let me write down the question. So it's so this is the first question, right? So it might extend or like more than 1 hour. Okay, uh, just that we want to understand more and more problems. So I hope everybody is comfortable with that. All right. So this is the first question. Okay, I won't give you the which question which exam it is, but after you solve it, then I'll tell you what the exam the question is from, which exam it is from. So the particle P1 is confined. Particle P1 is confined in a one-dimensional. Now you can also write along. You can write it down. Okay, because if it's in your copy, then it you'll be able to revise it properly. Otherwise, if you wait for the notes for my notes to come in, it's sometimes not useful. Okay, so it's better if you write down the questions. With walls, okay, at x equal to plus minus 1, another particle another particle another particle P2 is confined in one dimensional, and by the time you write down, also understand the question what it says. All right, so the time is not wasted at all. So one dimensional infinite potential well, and if we were in a class setting, we would have also written down the question on board. All right, so in that way we are not wasting any time. All right, so with walls at x is equal to 0 and 1. Okay, so these are some unit 0 and 1 and plus minus 1. Comparing the two particles, okay, P1 and P2. So one can conclude that all right, first point is A, the number of nodes, all right, in the nth state, in the nth excited state, all right, of P1 is twice that of P2. This is the first point. Second option is, now I'll just do this thing. The number of nodes in the nth excited state, okay, of P1 is half, okay, that of P2. All right. And C option, the energy okay, remember the problem which we did yesterday regarding the sine cube x sine cube wave function was there. The wave function was given to be sine x cube, not sine
Yes.
cube, sorry, sine cube pi x by l, right? That question was from CSIR 2014. All right. So whatever the questions I'm doing, even if there is no label on it, sometimes I forget about the labels. Okay. So those are all from previous years. All right. So the energy of the nth level of P1 is same as that of P2, right? And D option, now the same statement but written in a different way. Okay, everything is same, of P1 is 1/4 of that of P2. 1/4 of that of P2. All right. So this is the question. And so what to do? So you have two things you need to say see that there is one quantity which is the number of nodes, okay, in the nth excited state, and there is another thing which is energy of the nth level. Okay, two quantities which we are looking for. All right. So any guesses, anything, how to proceed?
P1 is
So,
symmetric and P2 is asymmetric. And
so option B.
P1 and P2 are particles, they are not asymmetric or symmetric. The infinite
matlab, sir,
potential,
I mean that
the particle,
the
the
state,
potential, the potential, not the state. The potential is symmetric.
potential, asymmetric and symmetric potentials, and width is 2 and width is 1.
Fine, good observation. Then,
So option D is correct.
okay, so let's see. So in this case, what happens? Is my screen visible?
Yes, sir.
Okay, so there was some glitch. So in this case, you can see that, let's talk about the number of nodes. Okay, so we know that for 1D box, we know that psi n has n minus 1 node, be it any potential, asymmetric or symmetric. Okay, so now in this case we see that the number of nodes is independent. Number of nodes is independent of size of box. All right, and this is clear. Now let's write down the energy. Now in this case we can say that what will be the answer then for this part? Now in both case, if you're talking about the nth excited state, the number of nodes will be both same,
Same,
right?
sir.
So number of nth excited state, now if we write down the statement, the number of nodes in the nth excited state, okay, of P1 is same as that of P2, right? So this is this is wrong, this is wrong, this gone. Okay, so let's talk about the energy. Now energy is what? Energy in both the cases, if you write
Is
down,
inversely
M square,
proportional to length square.
yes, very good. So we have this thing that 2m, and this is the width. Okay, this is the width. So if you write down EP1, this will be n square, okay, h cut square pi square by, you have 2m, this is 2 square, right? And if we write down for EP2, energy for the P2, n square h cut square pi square divided by 2m. Now this is 1 square, right? Now if you divide them, so what do we get? If you take the ratio P1 e P2, you'll get is 1 by 4, right? Which means EP1 is equal to EP2 by 4. So the correct answer is D option. And this is a question from TIFR. Okay, this is 2010. All right.
So can you explain the nodes point again?
See, we saw that the nodes, if we draw the wave function and we plotted the wave functions, right, for the asymmetric case, and we saw that the number of nodes of a given wave function is equal to the n minus 1 node. If it's a ground state, that is psi1, okay, because n starts from what? N here starts from n equal to 1,
1.
2, 3, all right, like this. So psi1 means ground state. Ground state will have n minus 1, 1 minus 1 node, means a 0 node. Psi2 has 2 minus 1, that is 1 node. Okay, psi3 has 2 nodes. Okay, so this will be true for asymmetric case also, symmetric case also. All right, you can plot the wave functions because we had like even odd, even odd. Okay, this alternate form was there. All right, so if you plot the wave function in the symmetric box also, you'll see the same pattern. All right. So, and it also does not depend on the size of the box. Okay, the number of nodes does not depend on the size of the box, and not on the symmetry or asymmetry of the box. All right.
Sir,
Yes.
sir, is this statement that psi n has n minus 1 nodes and number of nodes is independent of size of box? Sir, is this statement valid for 2D and 3D potentials also?
2D and 3D potentials, yes, of course, it will be pattern. The pattern will be same because see, we have to see, because see 1D it's clear to see the pattern.
Yes, sir.
But in
Yes, sir.
but in 2D, if you see the wave functions, it has 3 components. Say, for example, if you take the 3D box, okay. So in 3D box, you'll have no nodes. You have the components are, if you have 3D box, the way ground state wave function has 3 components, like the sine pi x, sine pi l. Okay, then you have sine pi y by l, and then you have sine pi z by l, right? So in that case, you'll see that if you plot the graph, if you are able to plot it with some mathematical software, okay, so there won't be any node because there is no point between 0 and lx, 0 and ly, and 0 and lz that it will go to 0. Okay, so in that case, there will be no nodes. If you talk about the this thing, so it depends. Like you have to check. Okay, you have to check. Now this does not see the number of nodes are independent of the size of the box. This holds true for any box. Okay,
Yes, sir.
number
Yes.
of nodes does not depend, like the number of nodes does not depend on the size of the box. This holds for everything. But the statement that psi n has n minus 1 node, you have to check. We have to check one by one, like then make a general statement. All right, so I have specifically written this thing. That's why I added this thing for 1D box. All right, so you have to just check whenever you have been given any system, you have to just write down the wave function, the general wave function, and try to, you cannot plot to 2D and 3D by hand, but what you can do is you can put wherever the psi is 0. Okay, so in that way you can get the nodes. You have to solve for psi equal to 0. All right.
Okay, sir.
So the next question is, so I'll discuss whatever comes in like the way. Okay, let me give you some more examples. So this is one question. Now there is this question that yeah, this is the question from this thing that you have a free particle, a free particle of mass m, is confined to a region of length L, confined to a region of length L. Okay. The de Broglie wave associated wave associated, all right, with the particle is sinusoidal in nature as given in the figure, as given in the figure. All right. Now the energy of the particle, is, okay, so it's a numerical type question, and the wave function looks like this. So this is L, and yeah, this passes through these points. Okay. Now the labels are same. Like, forgive my drawing. Okay, the maximas are same. So tell me, a free particle of mass m is confined to a region of L. The de Broglie wave associated with the particle is sinusoidal in nature. All right. So this is the wave function they're talking about, the de Broglie wave, because the wave function represents the de Broglie wave. All right. The energy of the particle is. So how can you tell what it is?
This is the graph of psi3.
How do you know that?
So we
Sir, two
plotted this.
nodes.
Yeah. So we take, say this is, there are two nodes. Okay, nodes is equal to 2. So we know that if we know that this, if you put, so we know psi n has n minus 1 node. Okay, n minus 1 node. So if we have so in this case the number of nodes is equal to 2, so n is equal to 3. So this represents, this is psi 3. Okay, and the quantum number is 3, and so what will be the energy? So E3 is equal to 3 square pi square h cut square. Now what is the length of the box here? L, right?
L, sir.
2 ml square. So this is not a numerical type. There's some missing part here. Okay, so let's keep it as a question mark. There must be some part, okay, to it, so that we can just put the numerical value. So this is a question from IITJAM. Okay, this is a question from IITJAM 2013. All right, easy, right? Now let's do this question. So were you able to solve yesterday's question? I had given
Yes,
you
sir.
homework. Everyone?
Yes, sir.
Good.
What is the answer for the parallelepiped?
Tell me the answer. What did you get?
11h square by 36 ml square.
Yeah, right. So a particle of mass m, is everyone getting the same answer?
Yes, sir. I too got that 11 square by 32
All right,
square.
good. So you have understood the thing. If somebody has a problem in any question, you can tell me. I'll solve it. Okay. If everyone is able to solve it, then we can skip the problem. Okay. So we have this potential. Okay, we have this potential, that is Vx is equal to 0 infinity. So this is x0. Now you see you can see that there are somewhere I told you that there is sometimes there is a inequality like this, and sometimes it's not there. Okay, so it varies from book to book or paper to paper. All right, so you don't have to worry about that. At some instant, at some instant, its wave mm, function its wave function is given by psi x is equal to 1 by root 3 psi 1 x. All right, so let's make it a different symbol for this. Let's make it phi. All right, so phi 1 x plus iota root 2 by 3 psi 5, sorry, let's make it phi 2 x. Okay, and psi 1 and psi 2. Okay, so and phi 1 and phi 2 and phi 1 x and phi 2, okay, are the ground and first excited state. Okay, and the first excited state respectively. All right, so identify the correct statement. Identify the correct statement. All right, so in this case you identify the correct statement. So the options given to you are, this is x L by 2. Okay, we have E, energy is given to be E h cut square by 2m 3 pi square by L square. Okay, B option is x equal to 2L by 3. All right, and we have E is equal to h cut square by 2m, and this is pi square by L square. All right, and then we have C is equal to x is equal to L by 2, and this is E. Okay, this is h cut square by 2m 8 pi square L square, and D option is x. Okay, x is equal to, this is 2L by 3, and then we have E equal to h cut square by 2m. All right, this is 4 pi square by 3L square. Okay, so you have the problem with you. So tell me how will you proceed? You have to find the expectation value of energy and position. Let's discuss how to proceed, and then you can do the rest of the thing as a homework. Okay. Any ideas?
So we did a question like this yesterday. We use that formula for the expectation value of energy, that Ci square into lambda I summation.
Okay. Yeah, that is correct. You can directly get, see, the energy eigenvalues are different for all, right? The energy, the expectation value is same for two of them. So you
Yeah.
have to sometimes apply this observation by observing the options. Okay, it's lengthier to calculate expectation value. because expectation of expectation value of position operator, because position operator, these phi1 and phi2 are not eigenfunctions of position operator. All right.
Yes.
Sir, but in 1D box, we found the expectation value of x is L by 2 now, sir. That we can
No,
apply.
but that is for a pure state. That is for a pure state, when a single state.
Okay,
This is
sir.
a superposition state. Okay, so you have to apply the whole thing. You have to apply the whole kind of like express like the basic formula. All right. So
Okay, sir.
all right. So in this case, you have to expand a lot of. You have to do a integration also. So I'll tell you how to do it. But then, if you are good in observing things, then you see that the energy eigenvalues are different for all. Okay, and these are energy eigenfunctions, right? So you can directly apply the formula. You can directly apply the formula to get the energy instead of calculating the expectation value for x. Okay, so that is why they have been placed
Sir.
before. Yes, tell me.
Sir, is option C correct?
Yeah, see, it's easier now. You already figured out what to calculate. It's better to calculate energy eigenvalue to solve this problem. So for energy, the wave function is normalized or not? The wave function is
Normalized, sir.
normalized, right?
Normalized.
So I think everybody knows how to do it. So you can check this by CI mod square, sum them. So this is 1 by 3 plus 2 by 3. Okay, so this is 1. So you can apply simply this thing, that's CI mod square and lambda I. All right. So in this case, what you have is, this is CI. All right. So this one will be 1 by 3 mod square. This is E1. Okay. Plus 1 by, sorry, not 1 by, this is root 2 by 3. Okay. So root 2 by 3 iota mod square E2. All right. So if you solve this, this is 1 by 3. Now this is E1 plus this is 2 by 3. Okay. And we have E2. E2 will be 2 square E1. All right. So this can be written as what? 8 plus 1, 9, right? So this is 8 plus 1, 9, 9 by 3. That will be 3 E1. Okay. So 3 pi square h cut square by 2 ml square. So are we getting it? So this is the A option, right? So this is this matches with the A option. So this is correct, because nothing we have to verify. Okay, all the energy eigenvalues are different. Okay, so if you are able to solve it, since these phi1 and phi2 are eigenfunctions of energy energy, so this will give you directly. They will give you the answer directly. But if you try to calculate the wave position operator expectation value, then you have to do the whole calculation like this. So this is psi x psi. Okay, in Dirac notation, if you write down this 0 to L, okay, this is psi star x. All right, psi. So you have to do the whole integration. Okay, so so in this case, you can just apply this. Wait. So this is psi star x operator. All right. So you apply the whole thing which is given to you as this is 1 by root 3. Okay, phi 1 plus iota 2 by 3. This is phi 2, and this is star. And x, we can, instead of x operator, we can write x. Okay, or you can keep it like that. So this is 1 by root 3 phi 1 plus iota 2 by 3 phi 2 dx. All right. So in this case, what will you do now? You can just see the how many terms you're getting. So in this case, it will be phi 1. Now these are real functions, so we can just keep it as it is, just that this will change. Okay, and this will remain as it is, phi 1 plus iota 2 by 3 phi 2. All right. So if you try to solve this thing, if you try to solve this, or instead of doing this, because the this integration for notation makes it very difficult to visualize things. So instead of doing this so many, because I wrote this to show you that this becomes complicated to follow. All right. So what you can do is, instead of doing this, you just use the Dirac notation at first. So that makes things clear. So we have psi, okay, we have psi, which is given by 1 by root 3. Okay, let me connect the cable to this thing, my laptop. All right. Now, so in this case, you have we can write like this, okay, in this format, Dirac notation. Okay, so this is phi 2. Now, if I can write down the bra vector, which is root 3, this is phi 1. Okay, now this will become minus iota, right? So minus iota root 2 by 3 phi 2. Okay, so this is what we have. Now if we write down x like this, so this will be 1 by root 3, okay, phi 1 minus iota 2 by 3 phi 2. All right, this is x 1 by root 3 phi 1, all right, plus iota 2 by 3 phi 2. Okay, so if you club them together, if you club the terms together, what will you see? So this is 1 by 3, this is phi 1 x phi 1. Okay, and then you have the next term will be, so I'm doing like this, I'm taking this along with this. Okay, and then we are taking the next term. Okay, we are taking the next term like that. Okay, so this is just a multiplication. All right, we are what we are doing here. So in this case, not a multiplication exactly, but inner product. So if we take this term and take this term, we get this one. If we take this term and this term, we get the next term. So this will be plus iota, this will be root 2 by 3 is phi 1 x phi 2. All right, and similarly we have next terms, which is minus root 2 by 3 phi 2, okay, x phi 1. All right, now this will be minus and the iota square, so the plus, this is 2 by 3. Okay, this becomes 2 by 3 and phi 2 x phi 2. Right, now you have this what you need is these values. We already know this value. Okay, we already know this value. What is the value for this? What is the value for this? This is what? This is the expectation value of the position operator in the ground state. Right, so we know that this is L by 2. Right,
Yes,
we
sir.
calculated this for any state. The position operator expectation value was L by 2 for a box size of 0 to L. Now this is what? This is what is the value for this expression? This is the expectation value of the position operator in the first excited state. Now this is also equal to
L
L
by
by
2.
2. So remaining is this one and remaining is this one. So see, you can see that since these wave functions, the phi 1 and phi 2 are real, so you can see that these two will give you the same result. Like if you want to write down this thing, if you write down this thing, this equation, so what will you write down? You'll write down this is root 2 by here, root 2. So let's write down the whole thing. This is sine pi x by L. Okay, this is 0 to L, and this is x operator. And then we have 2 by L. Okay, there will be a, say you want to take a conjugate, that doesn't matter here. Okay, and then you have here is sine 2 pi x by L. All right, dx. Right, everybody agrees on this. Now if you write down this thing further, you have 2 by L, 0 to L, sine star. Now star we don't require anymore because it's a real function, so we can simply write down sine pi x by L. All right, sine pi x by L, and this is x, this will be sine 2 pi x by L dx. Now if I try to write down this one also, phi 2 x phi 1. Okay, if I try to write down this also, what will you get? Okay, let's see. So this is root 2 by L sine. Now this will be 2 pi x by L with a conjugate, and then we have x. Now this is we are doing for the first time, so I'm showing it to you. We'll not do it this in the exam. We already know how will it look like. We should be able to visualize things for just by looking at the Dirac notation. So in this case, if you see this pi x, so what do you see? Are these expressions related? These two? This will give you what? This will give you 2 by L, 0 to L. Now this is sine, okay, 2 pi x by L. All right, now this is a multiplied, there is sine x inside and between. All right, now are these two integral same or not same?
Same.
Same, sir.
This is same, right? You can rearrange the things. There is no operator inside. Okay, you have whatever the operator was, you replaced it with this thing, the x. Okay, so these two are same. Okay, yeah, I could have already proven you without the integral notation. I could have simply taken conjugate this thing. Sorry, not the conjugate. The if I operate a dagger on this, so this will come out to be equal. Okay, these two will come out to be equal. So either you calculate either of them, you'll get the values for like, okay, you'll get the value. Okay, so just calculate one of them and you'll just multiply it by 2 to get this result. All right, so these two, instead of calculating two different integrals, you just calculate one of them, and just you don't need to calculate, you just see that this is negative, this is positive, this is negative. Okay, so this cancels each other, right? These cancels each other, right? If both the integrals are same, this cancels each other. So what do we have? We have is x. Okay, this will give you, so this is 1 by 3 L by 2. Okay, and what else do we have? This is 2 by 3. Okay, 2 by 3, and this is L by 2. All right, so if I take this thing common, so what do we get? L by 2. All right, is this clear to everyone?
Yes, sir.
Yes, sir.
All right, so these two integrals are where these two integrals were same, so we got this result. Okay, so instead of doing all these things during the exam, you could have just solved for energy and got the answer. And this was a question from IITJAM 2018. All right, right. Now let's give you a homework. Well, now this was a homework, but I already solved it, so never mind. All right. Now, next question is from Jest. Oh, I told you which exam it is. Usually what happens in class is sometimes I don't write down the which exam it is, and it will be, of course, somewhat beyond their syllabus. Okay, not beyond the syllabus, it will be within the syllabus, but it will be more advanced than what they're preparing for. And what they do is the students are able to solve it, and once they solve it, then I tell them what the exam is, and then they realize that they solved a CSIR-NET question or a gate question, even though they are at JAM level. So then they are very excited about it. Okay, so but if I give them that this is a gate and net exam question, somehow some of the students are able to like take the challenge and they move forward, but some students are, no, we cannot do it. Okay, it's beyond our capability. So the normalized eigenfunctions and eigenvalues of the Hamiltonian operate of the Hamiltonian okay, of a particle all right, confined to move between 0 x 0 and a in one dimension. All right, so in the one dimension R, you have been given this wave function. This is psi n x. Now there will be a root, this is 2 by a. All right, sine n pi x by a and E naught. All right, this is n square. Sorry, not E naught, this is n, right? Now they have given you the obvious thing, which you already know. Okay, so this is 2 ml square, ma square, not ml square. So the width is given to be a. All right, now in this question, now this is respectively. Okay, now this they are talking about the wave function and the energy eigenvalue respectively. That is fine. Now here 1 2 3 n is equal to 1 2 3. Okay, here n is equal to 1 2 3. Now again it's the obvious thing which you already know by now. Suppose the state of the particle is, suppose the state of the particle is psi x is equal to a sine, and this is pi x by a, all right, which is 1 plus cos pi x by a. All right, so this is the state given to you where a is the normalization constant. Okay, a is the normalization constant. Okay, a is the normalization constant, and if the energy okay of the particle is measured, is measured, okay, uh, the probability or to get the result okay, as pi square h cut square by 2ma square, all right, is x by 100. All right, so what is the value of x? What is the value of x? All right, so this is a problem from just 2018. Okay, so this concept I have discussed already before. I think some of you might be remembering this. So the normalized wave function, it's the first half is just description. Okay, you don't need to worry about this thing. You already know this part till here. Okay, now the question begins from here. Suppose the state of the particle is this. Now it's saying the particle is in the 1D potential, but it does not, the wave function, the given wave function does not match that of the this thing. Let's make it phi to separate the notation. Okay, so this is the eigenstates of the harmonic oscillator, sorry, not the harmonic, the 1D potential. Okay, which is the width is given to you 0 to a, and in this case the wave function which is given to you does not match with the general wave function, right? The wave function which we know, right? So that means the given wave function is what is a superposition state. All right, the given wave function is a superposition state, okay, which can be split into the known eigenfunctions. So let's see how to do it. So if I write down the wave function, do you want to try it, or I should I give you the answer?
Sir, we'll try for a minute, sir.
All right, okay, then don't look at on the screen. Okay, let me complete it, otherwise the audience on the who are watching on YouTube or some like online they'll get bored. Okay, so you keep doing what you're doing. After you're done, give me the answer and then we can discuss. Till then, I'll write down the solution. So did everybody get the idea what to do?
Yes, sir.
So you can split the wave function like this, and you can see some pattern. All right. So what you can see is this is what this can correspond to ground state, right?
Yes, sir.
And if we combine these two, if we combine these two using the trigonometry simplification we know, that will correspond to what? Now we can come, yeah, it can it so we can combine these two. All right, we can combine. So let's so this is you can see that this is some gs, this will give us 2 pi x. So this will correspond to what? First excited state, right? First excited state. All right, so you can, let's make this that way. So what we do is we try to make this in the format of what we know is a normalized state. So we have to divide, we need a factor outside and inside. So this is a by 2. Okay, let's divide and multiply by this thing. So it will be a, and we have is 2 by a, right? And this will be sine pi x by a. All right, then we have this thing that a, this will give you what? This will give you 2 by a, and we have now instead of, now we want to combine these two, right? So we have to multiply and divide by 2. So so there will be a 2 here and a 2 up, there will be 2. So if we combine them two, we'll get sine 2 pi x by a, right? I just directly wrote this thing. All right, so you can write this as, you can write using the notation what we have here is a. Now this will become, this thing will become what? This will be phi 1, and then we have a by 2, and this will become this this quantity can be written as phi 2, right? So if we just take these things together, so this will become a by root, a by root to a root a by 2, and this is phi 1 plus this will become a, and this is root a by 2, this is a by 2, and phi 2, right? Now we have a normalized all the basis base, the bases are all normalized. Okay, phi 1 and phi 2 are normalized, and we have this thing. Now what we want to do is we want to normalize the wave function. So what we can do is we can simply divide the whole thing, by the amplitude summation of amplitude mod square. So these are real numbers, so we can directly write down that this will be a square, a by 2 plus a by 4, a by 2. All right, and this is we have here is a by 2 phi 1. All right, a by, this will be phi 1 plus this is a by 2 and a by 2 root, this is what we have. And if we simplify it, what do we get? So this is a square, I guess. Yeah, so a will come out. Now a cancels out. Okay, a cancels out from here because there will be a here. Okay, so let's write it once more. So this is a, so what will we get inside? This is a by 2 plus this is a by 8. All right, and we have a root a by 2 phi 1 plus a by 2 root, this is phi 2. So this cancels out. All right, this cancels out. So what do we get? What do we get here? Now this one, now root a, we can take root a common. Okay, we can take root a common and then cancel this out. So root a gets cancelled. So what we are left with is root over, this is, this will be 8, and this 4 plus 1 5 by 8. Okay, and in this case we have 1 by root 2 phi 1 plus 2 root 2 pi 2. So if you solve this further, what you get is 2 root 2 by root 5. There is 1 by root 2 phi 1. This is 1 by 2 root 2 phi 2. All right. So this will give you If you multiply this, so what you get is 2 by root 5 phi 1 plus this will give you 1 by root 5 phi 2. So this is the normalized wave function which we wanted, all right, to solve our problem. Now we got the normalized wave function as we want. Okay, phi 1 is the ground state and the first excited state. Now the question says, if you look at the question, it says that the energy is measured, the energy of the particle is measured, and probability to get the result, they want the result, the measured energy, to be this pi square h cut square by 2 ma square. All right, so this is they want, okay, this is what they want, that if they measure this, if they measure the energy and they get this, what is the probability of measuring this energy. Now which state is this, which state is this, which state it will
Ground
correspond
state,
to?
sir.
This
Ground state.
this energy will correspond to ground state. All right, now we have seen earlier when we were doing, we introduced you the vector, like how the this thing, the superposition thing, that if you write down the vector as 2 I cap plus 3 j cap plus 4 k cap, and if I want that, what is the component of a along x-axis?
2, sir.
So how do you do it? You take a dot product
Dot product.
with a I cap. Okay, so you get 2. Similarly, if we have this wave function, if we have this wave function which is root 2 by 5, this is phi 1, okay, and this is root 5 phi 2, and we want, I have already done this, I have already done this in theory, I didn't do the problem. So if you want to find out the what is the probability of finding the ground state, if you make the measurement, and what is the probability that you will get the ground state. So what they are talking about, so they are talking about this thing, that C1 mod square. All right, C1 mod square, how will you get it? That is, you have to do the inner product, but the dot product here, this dot product, it converts to an inner product in this case. All right, so inner product with phi 1, okay, of the total way, the superposition state, okay, this will give you the probability of measuring the energy to be this ground state. All right, so what do you get here? Just do this thing calculation, so it will, you'll simply get what you'll get 4, this will be root, if you do a inner product, so this term will give you 1, this term will give you 0, so what you are left with is 2 by root 5 mod square, this will be uh, what you will get, this is 4 by 5. All right, so, or what you could have done, there was another way to do it. Okay, instead of doing this way, you could have done it another way. Okay, right, so you have been given this thing, and you have been given that this is equal to x by 100. Okay, this measurement, this ci mod square, c1 mod square is equal to given to be x by 100, okay, which is 4 by 5. So if you write this down, so this will become 80. Okay, so the answer was 80. All right, in this case. Now there's another way to do it. Now this was done so that you already, what you're familiar with is you can do it. Now this step you could have directly applied in the very first place. This step you could have directly applied in the very first state, because you would already know you want what is the C1 mod square. All right, you want this quantity, that if you measure the energy and you get it to be ground state, what will be the probability of that? Okay, so you wanted to measure this one, so if you write down this thing using the integration notation, okay, if you want to write down this thing, so but let's calculate this thing. Now this is a very important problem, okay, from the number of concepts we are using. So in this case you want to write this, so what you'll write is phi 1 star, and this is psi. All right, so this is 0 to a, and we have the phi 1, we know phi 1, we want phi 1, we want to do this inner product with phi 1 because the energy corresponds to phi 1, right? So that is why we are doing this thing. Now this will give us the, we have to see that whether it's normalized or not, we have to use the normalization thing also. All right, so because this wave function might not be normalized, so you have to do the normalization thing also here, you have to normalize this wave function. So that is all, that will also become the same, like effort will be the same, but you can do it this way also. All right, so you want to put this, see, we already know phi 1, okay, we want psi to be normalized, this should be normalized psi. Okay, this should be normalized psi. So you could do this way also. So you normalize the psi and then put it here and then solve the integration. So you have two integrations to solve. Okay, and the method which I used, you didn't need any integration here. All right, you could have that, like it's just algebra. Got my point? So you can try this method 2 as a homework and see that it works. Okay, you just find out the normalized psi, okay, instead of the given psi. All right, so the normalized, let me write it down. So this is a sine pi x by a. All right, this is plus 1, sorry, this is 1 plus cos pi x by a. All right, so you have to normalize this first. Okay, normalize this. Okay, just use the integration. Okay, just use this thing, right? The normalization constant method. Just put it in this integration and normalization condition and get the normalization constant. Okay, and then solve it this way. And then after solving this, you're like normalization. After doing normalization, you put it here. Okay, after normalizing this, you put it here, and then after solving this, you put it here. This is the answer. Okay, this will be the answer to your question. Not exactly, because you have to map it to x by 100. Okay, so whatever it is. Got my point? Shall we move ahead? Hello.
Yes, sir.
Okay, I thought everybody fell asleep.
No, sir.
uh, so this was the question, and then let's talk about this. That so this we have done. So let's do some problems from GATE and CSR. All right, this will be of the same level as we have already covered. Okay, so this is done. What we were looking for is yes, any questions? Tell me. Okay, so this was done. This was now let me give you a question which you should try, and I hope everybody will be able to solve it. Okay, this says that the ground state energy okay, of a particle of mass m in the potential Vx is equal to V naught cos hyperbolic cos x by L, and L and V naught where L and V naught are constants all right, and we have with V naught. Now this thing I was reading a biography on Grigory Perelman. Okay, one of the mathematician who denied, like he didn't accept the Fields Medal, not the $1 million prize by Clay Institute. Okay, for solving the Poincare conjecture. So from that I realized that like in some countries there is a culture of there's a coaching related to this thing, chess and maths. Okay, they have a separate coaching other than school, not this coaching for our entrance exams. They develop they try to get good teams, they try to build good teams for the international olympiads. Okay, now here you need to first be good by yourself, then you'll be selected for such camps. but in there you don't have such barriers. Okay, you can practice and join any club you want. But in physics there is no such coaching, like as in maths and chess. All right. So because this is also problem solving, like you develop the problem solving ability by attacking the problem in the best way possible. Okay, but that is also not feasible to one coaching. All right. Because there's cost issue involved. So this is CSIR December. All right, this is 2015. Now this you could take as a homework problem. All right, so that we can discuss some more problems here. Now there's a question from, will you be able to do it? How will you proceed? Now this is not from one day box. All right, this is not from one day box, or is it? No, it's not from one day box. This is a general question from previous papers which we discussed, previous theory which we discussed. All right, so there's another problem. How will you proceed with this problem? Any idea? This question. Hello.
Schrodinger equation.
Yes, Schrodinger equation. Okay, solve the Schrodinger equation, you'll get the answer. Now we have already done this thing. Okay, we have already done this kind of question. Now this is a practice problem. The wave function of a free particle, of mass m, all right, constrained to move. Actually I don't have time, like somebody was saying in the YouTube channel that, sir, after doing this quantum you start with EMT. I said I'll try, but I like it, I do not have that much time. I would like to teach all the subjects, but then I do not have time. So this time I'm doing quantum only. Now minus L is it possible for you guys to do a 2-hour session?
Yes, sir. From 3 to 5, sir, like that.
3
Yeah,
to
it
5 is
could.
okay.
No, because see, looking at the screen for such a long time is very uncomfortable to eyes. All right, and that's why I'm putting it to be 1 hour. Okay, but then also I need to.
So that is not a problem for us, sir.
Okay. So I'll now I'm talking I'm going for 1 hour for each day. Then I'll say I've already increased the number of days in a week. Okay, so I'll slowly increase this thing, the hours, and I'll complete like within time.
Okay,
So
sir.
It'll be good. Then we'll get a lot of time for revision too.
Yeah, I understand that.
Sir,
But
and we are
then-
getting confidence on this paper, sir. Quantum
Yes, sir.
mechanics.
Even I'm getting confidence on quantum mechanics.
No, I told you, no, like if
Sir, I
Hmm.
went to the papers of IITJAM, sir, and saw the questions on quantum mechanics, and I was feeling like it was very easy, sir.
I solved a lot of problems of commutator related in asked in gate, and I was able to solve.
Great.
Confidence is building up, sir.
Yes, see, you guys are from what I see is you are hardworking students. So just follow my whatever I told you. Follow my advice and follow my lectures. I'm definitely sure you'll get in. Yeah, of course, I'm not doing all the subjects. Okay, but I am telling you that what I am teaching, if you are very sincere enough, which you are from what you are doing, and I'm able to see that from your answers what you're giving in the class. Okay, if you keep this till the exam, okay, you should definitely get good result. But yeah, don't get too much excited. All right, because there might be situations where you might come across questions which you have never solved it. So stick to your basics. Whenever you see such type of problems, just break it down to basics. Okay. So good for you. I'm happy to hear this progress. All right. So now someone was also saying to me to start mathematical physics. I said, yeah, I can do all of them, but there's the time. Time is the issue. All right. So this is a problem which we have already solved. This kind of problem right now. Okay. This is a question from June 2019. CSIR June 2019. All right. So this is a similar problem if you look at it, okay, which we already did for JAM, this thing, earlier problem which we did for JEST, okay. So this is a similar problem to it, like same as the previous one almost. Thus the wave function is given to be different, okay. So you need to like, I want you to do it as a homework, right? So if you face problem, then we can discuss. I think you'll be able to do it. All right. So shall we stop here? Hello.
Yes, sir.
Let's stop here and then see, the thing is just a little bit of quantum mechanics each day gives you a good score. Okay.
Okay, sir.
All right. Thank you for watching. Have a great day. All right.
Thank you, sir.
Thank
Take
you,
care.
sir.
Bye.